Hey guys, today we are going to discuss about exchanger analysis. Now often an engineer finds himself in two positions. First one, he will have to select a heat exchanger which will achieve a specified temperature change in the fluid stream of known mass flow rate, or he will have to predict outlet temperatures of the hot and cold fluid streams if a specified heat exchanger is already selected. So, in order to tailor these two demands, the analysis of heat exchangers is divided into two methods. The first one is the logarithmic or log mean temperature difference method. We also abbreviate it as LMTD method. And the second method is the effectiveness NTU method. Now the LMTD method is best suited for the first task, whereas the NTU method is best suited for the second task. Before we go into details about the heat exchanger analysis, we need to understand certain assumptions based on which the analysis is carried out. The first one being, the heat exchanger is said to operate for long periods without any change in operating conditions, so they can be modeled as steady flow devices. Second of all, we assume that the mass flow rate of the fluid elements remain constant, that is, a hot fluid as well as a cold fluid will have mass flow rate which will remain a constant. Properties such as temperature and velocity at inlet and outlet tends to remain the same. Kinetic and potential energy change is negligible. Importantly, the specific heat of a fluid, which we know changes with respect to temperature, is treated as a constant at some average values. Now this will lead to certain errors. Lastly, axial heat conduction along the tube is usually insignificant, and outer surface of the heat exchanger is assumed to be perfectly insulated. So under these assumptions, we are going to define certain terminologies. Firstly, the heat exchanger should obey the first law of thermodynamics, that is, energy is to be conserved. So the heat lost by the hot fluid is supposed to be gained by the cold fluid. So that heat transfer rate, we can express it by the general formula mCp delta T. So for the cold fluid, I can write it as m dot C Cpc Tc out minus Tc in, and for the hot fluid, I can write it as m dot H Cph Th in minus Th out. Now here the subscript C and H stands for hot and cold fluids. Here m dot C and m dot H represents the mass flow rate of the cold fluid and the hot fluid. Cpc and Cph represent specific heat. Now one thing to note is that in certain textbooks you can find the Cpc and Cph in capital letters, but mostly specific heat is mentioned in small letters, Cp, small cph and small cpc. Alright. So in this heat exchanger analysis, it is often convenient to combine the product of mass flow rate and the specific heat of fluid into a single quantity. This quantity is called as heat capacity rate and is represented by capital letter C subscript H and C subscript C, where CH and CC is nothing but the product of mass flow rate and the specific heat. Now again, the specific heats are usually represented by small letters. So by including this definition of heat capacity rate into the heat transfer equation, we can have the heat capacity rate as Q dot equal to Cc into Tc out minus Tc in, and the same Q dot in terms of hot fluid will be Ch into Th in minus Th out. Now by first law, these two heat transfer rates are similar, but for the temperature rise and temperature fall. That is, the hot fluid will experience a temperature fall, whereas the cold fluid will experience a temperature rise. For this two to be equal, one necessary condition is that their heat capacity rates should be equal. That is, for the delta T occurring in the cold fluid to be equal to the delta T occurring in the hot fluid, it is necessary that the heat capacities of the two fluid be same. That is mentioned here in the diagram also. So you can see this delta T remaining constant if and only if CH is equal to Cc. Now we have completed the basic terminologies associated with heat exchanger analysis. For any doubts related to the lecture, please comment in the comment box and I will reach back to you. So see you in the next lecture.